as this is the now new central equation of motion in this new picture, that is the Heisenberg picture, we have to develop certain further properties in order to be able to use it, at least as a first step in determining the time dependence of that chosen observable. And then once that is obtained, we have to ask the physical questions to be answered eventually, of course. The very nature of the questions depend on the nature of the problem. Here, the first question which is to be addressed is, what is the time dependence of the H? H was originally chosen from the Schrödinger picture as all the things, but we haven't put a label to it. Actually, it should have been, if we were naive enough, be trying to be over careful about the notation, we have to put an HS label to this, and then transform it in this manner. Well, you may say, well, that's really childish. Of course, I know. What I'm doing is childish. But it is to be really understood properly. We started with a default picture. Hamiltonian was from that default picture. Naturally, I should have been expected to put the label HS. And the transformation was again based on that H in that picture. Therefore, it should have been also properly labeled as such. And HS commutes with the exponential of HS, as is the case for any function. Therefore, you can jump this over. And then this operator and its inverse gives you the identity. So you have the HS. Well, that was the implicit reason why we were not really putting any label on the H. H is the same in all pictures. H, whatever H is in the Schrödinger picture, it is the same in the Heisenberg picture. H is the same in all pictures. Same in both pictures. Notice that I pulled back the word all and instead replaced it with the both. Because you'll have a third picture eventually, which will be called the interaction picture. There, the full Hamiltonian and the time-independent part of it are really subtle things. So here we are talking about the Schrödinger and Heisenberg, and this H is the same in both pictures. Nice. Implying that H is time-independent. So H is a very special entity in the Heisenberg picture. All observables gain the time dependence, they carry time the dependence, but H is not. So it's time independent. Well, this should have been emphasized, really, although it's a trivial statement, and the demonstration is trivial, statement is trivial. H is time independent. It was so in the Schrödinger picture. It is still so in the Heisenberg picture. That's very nice. Second, in order to make use of those new equations, which look quite nice formally, but in order to make operationally proper use of it, you need the following statements. What are the new versions versions, of course, are of the algebra xi, xj is equal to 0, pi, pj is equal to 0, xi and pj is equal to ih bar delta ij. Remember, in the last lecture we have worked it out. We said this is sort of, by definition, it's sort of, if you want, in a mathematical axiom, the commutation of the different components of the position operator is because of the very definition of the reference frame. We take them to be non-commuting. It's at the background of most of the physics that we have been doing. But although there are some recent works on taking non-commuting coordinates and construct non-commuting physics, non-commutative geometries, etc. But that's a new research frontier. But here, till now, the conventional physics is based on commuting position operator components. This is obtained by working out the translation in space and saying that this transformation is a abelian, well, it turned out that it's an abelian group because to translate in two steps along x and y first and y and x next, which takes you to the same point eventually to be translated to. The physical equivalence of this translation led to the commuting of the generators of the translation. Well, generators of the translations we have identified as 1 over h bar times the p. So this also follows the physical symmetry of the space. Okay, homogeneity of the space, which is obviously, we said we have translation symmetry which leads to momentum conservation. We have translation symmetry in time which leads to the conservation of the energy. These are beautiful principles. And this also we have been able to work out using again the transformation and the behavior of the position under the translations led us to this last commutator. This is an algebra. It's called the Heisenberg algebra. And in principle, you may think that the quantum mechanics is a representation of this algebra. So it is particularly, well, it's crucial in the Schrödinger picture, and it's particularly crucial in this new picture because in order to carry out mathematical manipulations in the context of that new equation, as both H contains momentum squared and potentials, which is really the arbitrary functions of x. So for the first term and second term, the A observable in question is usually taken to be either the position or the momentum. Therefore, we need this algebra. But question is, how is it now in the Schrödinger they go to these. And P, the same for P. You take these time-independent entities. I put the super labels now because I need room for the vector coordinates down. So Schrödinger picture, momentum operator goes to Pi Heisenberg T. Question. Xi with xj is 0 because they were independent of time. There was no ambiguity on the meaning of that commutator. Now there is an ambiguity on the meaning of the commutator because I may think of the following. They are both Heisenberg now. Let's make the following convention. In order not to complicate the notation too much, when I put in the time dependencies, I will suppress the H label indicating that it's in the Heisenberg picture. Because having a time dependence naturally means that it's in Heisenberg picture. What is your first hunch? This should be 0, right? It is not. Life is tough. Things are not that trivial, really. Let's demonstrate this for any arbitrary operator now. Of course, it's not true. We will demonstrate what is true. Now, it is not true. And you cannot measure the position operator components at different times simultaneously. Well, you may say there is not a simultaneity problem in here because the value in here and the value in there of course, refer to different times, so I'm not really talking about simultaneous measurement. Well, of course, that is something, but you may say, well, I will demonstrate first, let's wait for it for a few minutes, but if you really get this answer, then obviously, when you go to for instance, even the same component. Let's go to one dimension to make life simple and trivial. Well, if these do not commute at different time, yes, I will answer just a second. When you take the uncertainty products of those x's at different times and apply the Heisenberg uncertainty principle, you will get an expression of this sort. It is difficult to interpret. I invite you to think of it on your own a little bit. If need arises, we may discuss it in the class or during the recitation. Yes?
So can we say that it will be 0 if T2 will equal T1?
Yes. Let me demonstrate that. So these have rather strange consequences, and you may wonder what is going on in here. For example, how do you represent a free particle? We will discuss those in detail eventually. I will in the third hour, perhaps. You may take it as a plane wave, right? A free particle. Because the Hamiltonian is p squared over 2m, it commutes with the p. So therefore, that free particle Hamiltonian and the momentum have common eigenfunctions. And we know what the momentum eigenfunction is. It's I over h bar px. It's the same for the energy, so it's e to the I over h bar px. The plane wave is the free particle solution. Now, free particle solution is exotic because that label p is telling you that it's a definite momentum, which means definite wave number. Well, you use the Heisenberg uncertainty, it of course should mean that x is fully uncertain. Fully uncertain. If p is certain, 100% known exactly, x is fully uncertain, so you don't know where the particle is. But it's only natural. If it is plane wave infinitely extended, you say, where is the particle actually located on that wave front which has infinite size? It could be anywhere. So it's fully uncertain. What is a sort of more physical, sort of close to reality description of a free particle? You may think of constructing a wave packet, which is really composed of superposition of infinitely many components, each of them having a well-defined label, but when you put in those infinitely many components in the form of a Fourier series with proper wave factors, you may take this wave packet as a more realistic description of a particle, but it's not point-like, it is an extension. And the extension is what you call the delta x. Then you may ask the following question. As this particle evolves, does the size of the packet changes? That is, does delta x depend on time and it becomes larger? And you can work it out. I invite you to do it on your own. If time permits, I'll ask the teaching assistant. Apparently, there was no interest in having a recitation, so we decided not to have one before the exam. So the wave packet really swells. When it moves a couple of meters, and you had to start with a local, very local wave packet in here, say at the size of 10 to the minus 10 meters, Fermi size, and let it evolve. It's free, there is no external agent, but if it is free, it swells. It becomes a huge size entity after a couple of meters. This is really an indirect way of saying that there is this uncertainty and this really swells. And that is also a challenge against this uncertainty relation. I don't want to call it simultaneous measurement, because one is at t equals 0, the other is t. You are not really measuring them simultaneously. So when you're talking about quantum physics, you have to use a careful language, really. You have to be very careful on the language you are using. Otherwise, you'll make mistakes. Let me do this in more general terms. Let me pick arbitrary A, observable, and let's call it H, and let's take it at T1 and BH of T2. Let's talk about this commutator. And let's see how is it going to be related A and B, which we were cleanly talking about when we were discussing in the default picture in the previous lectures, right? We were saying we have an operator A, we have an operator B. If they commute, they will have simultaneous eigenfunctions. If they are not commuting, we will have uncertainty relation in terms of their variances or uncertainties, etc. Well, that's a clean language, but here it is really not that clean, right? Because in principle, I can think of taking those operators at different times. Being different is good enough or worse enough than you think of them and taking at different times. The answer, let's reveal the secret. The only meaningful things that we are going to talk about are equal time commutators. When you think of Heisenberg pictures, and when you think of algebras of this sort, you will think of equal time commutators. That's even so true when you go 2 steps forward, go to the quantum field theory. You'll see that there will be fields in there. Field and their momenta, they are of course infinite dimensional vectors and operators. And their commutators will also be defined at equal time. Equal time commutators. That's a secret, the sacred terminology I need to be underlined. But let me go to that point cleanly and systematically. How do I go from this ugly and complicated looking expressions to a meaningful clean ones in the following manner? If you take this commutator, it is what U dagger in the notation that we have developed. A, let's drop this U dagger of T1, A U of T1, U dagger of T2, B U of T2, right? That's the definition of that commutator, ugly commutator that I have written there. What is the commutator? The first term times the second minus the second times the first. So what concerns us is this product of neighboring things. If they are not the opposite of each other, the inverse of each other, that is, if the second factor U dagger is not the inverse of the first, you don't get anything. You get an ugly beast. The first times the second minus the second times the first. What is it? Well, we don't know. It is a ugly beast. To make sense out of this, we have to ensure that this is the inverse of it. The only way that this could be done is by identifying the T1 with the T2. If so, the neighboring terms U dagger from right or left the same, they become the inverse, cancels, and you get the following then. U dagger T1 AB U T1 when you take the T2 equals with T1. Correct? So whatever this commutator is, it is transformed in the usual manner. So we get a new lesson now. The new lesson is that Schrödinger picture operators transform as such to the Heisenberg picture, and commutators also transform the same way under U. A Schrödinger commutator, B Schrödinger transform U dagger T, A Schrödinger, B Schrödinger, U of T. If you remember now this rule, which is simply obtained, then what is the new version of the algebra is more or less trivial, right? If you take A as the xi, B as the xj, xi, xj in the Schrödinger picture is 0, so this is 0, that becomes 0 in the Heisenberg picture if they are taken at equal times. Then, if it is P, Pi, Pj, Then if you take them at equal time, it transforms that way. Pi pj is 0, and the pi of t and pj of t is equal to 0 as well. If you take one of them to be xi, the other to be the pj, xi pj is I h bar delta ij times the identity operator. Again, it jumps over the identity. You get the I h bar delta ij. So we obtained that beautiful result. Let me write it. Heisenberg algebra is valid for equal time algebra. So we have demonstrated in very general way, xj of t is equal to 0, pi of t, pj of t is equal to 0, and xi of t, pj of t is I h bar delta ij times the identity operator. That's nice. So it is this algebra that we will use in working out that expression there. Question. Well, this is at time t, that's at no time. It's time independent. How do I work out the algebra? This is so strict. If they don't come at the same time, they do not obey anything like this. They obey some ugly beast, which has no meaning. It's not even wrong. It's nonsense. Only at equal time they make sense. So how shall I work it out? Any comments on that? Well, if it is the equal time algebra, which will help me in decomposing, I will do that immediately. I will apply it to free particle. You'll see what do I mean. Then I have to take this at the time indicated in here. This time dictates you that h is to be expressed at that time. You may say, why? Isn't that time independent? Yes, that's why I'm doing it anyway. It is time independent. It has the same value at any time. I can take it at any time I like. I take this to be at the time which the second entry indicates. As h is time independent, I am free to take it at any time I like. And that time I like very much is this time, because it makes all the commutators appearing in here to obey the equal time commutation relations that I have there. So let me illustrate this. I hope you really appreciate this particular point. It's a beautiful point. Therefore, let me illustrate this on the free particle. Example. To make life as simple as possible, I will take 1D free particle. Well, of course, 3D free particle is equally simple, but you have to worry a little bit about the indices of the vectors. Well, anyway, by now you must have been experienced enough. But to illustrate the point, I'll take that to be one-dimensional space, online, really. What is the free particle Hamiltonian? Free particle Hamiltonian is p squared over 2m. Well, OP, if you want, operator, right? Squared. For instance, you may wish to solve the Schrödinger equation for this. Schrödinger equation written for the wave functions, which are the coordinates in the positions, in terms of the position space eigenvector basis, position operator eigenvector basis, or you can try to solve the same problem in the Heisenberg picture, whose equation of motion is that. The first step is take A to be x and then p. These are the basic variables, right? Basic dynamical variables. They're also the central operators in quantum theory. So if I take this, dxh of t dt h xh of t. That's the equation I over h bar. Okay, that's the equation of motion I need to solve. Write the Hamiltonian. Then put the time in. I do it in two-step. I assign the time t same as I could have assigned it to any time, but the only time which is worthwhile is this time. Then the right-hand side becomes I over h bar 1 over 2m ph bar squared t xh of t. You see, I'm freely moving the h label up and down. I could even drop it because I say as they are time dependent, that must be in the Heisenberg picture. It is the cumbersome notation. Sometimes you have to bear with this notation, not to get confused. So how do I work it out? This commutator, there is the usual decomposition rule, A, B, comma, C. There's product 2 operated with the second. The first factor to the left, second factor to the right. And you decompose this in the following manner. By now you should be experienced enough. Okay, plus, I'm decomposing it. Please just don't write the definition, because in the exam papers, when I put this in, they write p squared times x minus x times p squared. What do I get out of this? Well, if I decompose this, I can use the basic. Minus IH bar. Minus IH bar. Delta IJ, I don't need it because it's one-dimensional. And the minus because x with p is IH bar, p with x is it's anti-symmetric, minus IH bar. So h bar over I over h bar cancels. There are 2 cancels, so 1 over m. Let me use white further. 1 over m ph t. What is it? dxh t dt. What is this? Well, it's a beautiful recovery of the known expression that momentum is the mass times the velocity. It reproduces in the context of quantum theory, so it's the correspondence principle is verified, right? In classical physics, momentum, in terms of dynamical variables, momentum is the same as mass times the velocity. So this first half of the Heisenberg equation reproduces that expression in terms of the operators, that relationship. Momentum operator is mass times the velocity operator, beautiful. So it's not a redundant or useless derivation. It is a very important verification of the correspondence principle. Then we continue with the other. We have tried the x, gave us this. So we'll try the p. Let's see what it gives. Okay, the second equation then is dph t dt is I over h bar h pht. This is p squared over 2m. First, no label because h is the same in Schrödinger and Heisenberg. So the natural place is the Schrödinger, no label. Now we say we'll take it to be at any time and go to the Heisenberg. Put this. Well, perhaps I have to introduce those labels with a different color so that I really put it by hand. It is me who is doing it. Because if it is different time, P's at different times do not commute, you get non-zero. Think of it. How interesting, right? How interesting. Could it be so simple? It is. Then P commutes with any function of itself. you get 0. It looks as if I am putting that at t to get 0. If I put something, I will not get 0. And I am free to put that other something as well. Think of it. Quantum physics has a lot of room for philosophical discussions. How do I know to get that right value? It is forced upon us, but I'm free to choose any other value as well. Then I will get something which is different than 0. Is this a paradox? I don't know. I'll leave it to you, okay? Think of it. Quantum theory is full of these kind of pleasant surprises. Lesson. dp dt is 0, so p is a constant operator, right? It's a constant, it's the operator itself, so its constant thing should also be operator. Constant means independent of the time. So I can take it at any time I like. What is the ideal time? This time, ideal time is t equals 0 if it's the constant. Notice that this time I take it to be at 0. Take at t equals 0. So it is p h of 0. So it's p, Schrödinger, or drop it. It is that constant operator is the p at the Schrödinger picture. So I have two equations. This first equation and this one. This was immediately solved to get that ph of t is just a p Schrödinger operator, however. So I can substitute this in here to solve the dx. Operator, Schrödinger picture operator. So let's integrate this to get the solution. X h of t is t over m p, well, operator, Schrödinger picture operator, plus a constant operator, because I'm talking about the xht operator, right? How do I determine this constant? I go to the t equals 0, xh of t equals 0. The first term is 0. Second term is that constant operator, right? So this constant operator is this thing, xh at t equals 0, which is nothing but the Schrödinger picture x operator. So finally I have the solution. xh of t is equal to x Schrödinger plus t over m p Schrödinger. These are all operators. Perhaps let's put that ugly label to emphasize that we are talking about operators. So I have solved the problem. X at time t is the x Schrödinger plus t over m p Schrödinger. Is this something that you recognize? Yes, this is really the free particle solution in classical mechanics. If you have used Newton's equations of motion, you would be getting this, right? X plus p over m times t. P over m is the velocity. If you go to the classic, compare with the classical, x plus vt, right? That's what that expression is. We have found it in the quantum theory in terms of the operators. Amazing. So this Heisenberg picture is built into it the correspondence principle. This one-to-one correspondence with the classical physics. Dynamical variables in classical mechanics and operators in quantum mechanics, however, that's still the thing, right? I will deviate from the book for a few minutes, perhaps a little more than a few minutes, to illustrate, to enrich the example, because eventually I will talk about the Ehrenfest theorem and the Heisenberg equation, and then eventually the behavior, time evolution of the eigenkets of observables. Well, we have this sort of opposite behavior. Let me summarize before moving into that next example that you feel more comfortable. It was trivial, more or less. In this case, when you go to a little less trivial example like harmonic oscillator and how do you deal with it in the context of Heisenberg picture, then we have to spend a few more minutes. But along the way, I have to remind you that in the Heisenberg picture, it is the states which are frozen, they do not evolve, it's the observables which do evolve. Well, in this Hilbert space, there are states, observables, other operators, unitary operators, which carry out the transformation between these states and observables. And there are also eigencats of the observables. It's a crowded space. There are many entities, really. It's like a zoo. There are states which are frozen in time, if I am in the Heisenberg picture version of this Hilbert space. There are cats. Naturally, what you would think that these cats are frozen in time as well, right? Because as the states, you can choose one of these arbitrary cats, which are members of these orthonormal sets. It's not the case. It is strange. The cats, if they are eigencats of an observable, as the observables are time dependent, those eigencats of the observables, they will depend on the time, despite the fact that states which can be expanded in terms of those bases, they are frozen in time. The basis vectors, which are the eigencats of Heisenberg observables, are dependent on time. I will work it out. It's a beautiful statement. And it shows how rich the mathematical structure of the quantum theory is. It again sounds like paradoxical. Is this really paradoxical? We'll work it out. But let me enrich this by going to the second example. Second example I will consider is, again, simple harmonic oscillator in 1D. 1D because I don't want to complicate the notation with the indices. So what do we need to start with? It's the Hamiltonian, the usual, p squared over 2m plus 1 over 2m omega squared x squared, right? That's the simple harmonic oscillator. And if I was in classical physics, I would have this potential. Of course, the potential is the same. I will have the same potential in quantum theory as well. The energy is the kinetic plus the potential. So at this point, this is the total energy, and this portion is the potential energy, and the total, this is the total energy, and that much is the kinetic energy. As you move to that endpoint, the total energy minus the potential energy becomes 0, kinetic energy becomes 0, thus it's the turning point, and it oscillates back and forth, right? Between these, for that particular E, for that particular value of the E, and these are the amplitudes, right? And the oscillation takes place in here. And if you go to different energies classically, and you can identify the amplitudes, etc. So in principle, when you go to the very bottom, then there is no room for oscillation. It rests, stays at rest. That is the basic difference between classical and quantum theory. You'll see that at quantum theory, even at the ground state, you'll have still an energy, h bar omega over 2. Therefore, that quantum fluctuation is an important thing. But here is the sort of this classical discussion is important, how you get turning points when the kinetic energy, that's the difference between total and the potential, becomes 0. Now this one, if I need to solve it in this new context, I will refer to the equation, write down the equation again, dAht dt I over h bar h ah of t, and A, I will take X, and P, that's the algorithm, how you approach the problem. And then you work out the dx dt, dp dt, and integrate. Let's do that. The first one is easy. Dx t dt, if you allow me, I will drop the H labels as they are depending on T, obviously. I'm in the Heisenberg picture. I over H bar h and xt. H is time independent. I'm free to choose at any time I like. I take it to be at t so that I can use the commutation relations, equal time commutation relations that we work out among the basic operators, x's and p's. So this is p squared t divided by 2m, and that's xt. You may say, how nice. As far as this x portion is concerned, it's the same as that equation I obtained for the free particle. Well, of course, it's only natural because it's going to lead you to the identification of the momentum as the mass times the velocity, because right-hand side comes as 1 over m times pt. How nice. You say, okay, it's the in compliance with the correspondence principle, it leads the known result that momentum is the mass times the velocity. Good. So that portion is always the same, except velocity dependent potentials for the electromagnetism. If there are velocity dependent potentials, of course momentum, that right hand side will be p minus e over ca. It's going to be the kinetic momentum then. Here canonical and kinetic moment are the same. Velocity, in the presence of velocity dependent potentials, canonical and kinetic momenta will not be the same, they will be different. The second part is a little less trivial. Let's work it out. Now I will focus here. I will do it there. dp dt I over h bar h pt. You may say, what happened to the second term? Well, it's trivial, I'm sorry. Sometimes I drop trivial terms, but in order not to make you feel uncomfortable, I have to add that omega squared, x squared. As we have put it at the same time, x squared and x commuted, that's why I dropped it. And that's why the presence of any potential didn't change the definition, or ordinary x-dependent potential, that is, definition of the momenta. So that didn't contribute, right? X squared and x commutes at equal times. If they were at different times, they wouldn't be commuting, obviously. So the same in here, p squared over 2m, taken to be, I use that fancy game of putting the t myself to be on the same as the other, 1/2 m squared, m omega squared. Did I make any? Of course. Then I would be flanking at freshman physics, right? M omega squared x squared t. We put that t. The first term this time commutes. If it wasn't for the second term, we would be getting 0 in the right-hand side and the constant momentum, etc., as in the previous case, free particle case. But now the presence of this changes everything. So I over h bar, move this constant out, x squared t pt. Being at equal time, I can use the algebra. X times x commutated with p plus x commutated with p times x to the right. So twice I h bar x of t. I carried out the commutation by heart a, b, comma, c. Decompose it, okay? That's it. So what is it? H minus I h bar over I cancels against this. 2 cancels. So you have m omega squared xt. So this is dp dt, dp of t dt. This equation, together with which equation? Together with this equation, need to be solved together. as we have done before, but it's less trivial now, because in the free particle case, it led to constant momentum. Now, P is m times dx dt. Substitute in here, d by dt of m times dx dt, right? I am substituting for P what I have obtained from there. That's the left-hand side. That's the right-hand side. M's cancel. So what do I get is the second derivatives. In the left-hand side, d squared x of t dt squared is equal to minus omega squared x. Move it to the left-hand side. Plus omega squared x of t is equal to 0. You say, oh yes, of course. This is the equation I am familiar with from classical mechanics. That's the equation I get for the x dynamical variable. It's the same equation for the operator, however. How do I solve this? I solve it by the same reasoning. X of t will be a C operator times C1 operator sine omega t plus C2 operator cosine omega t. If you want, you could write them as exponentials, plus and minus e to the I omega t, e to the minus I omega t, and decompose e to the I omega t as cosine omega t plus sine omega t. Rewrite it in this fashion. So it's simple mathematics, nothing to it. So how do I get the P out of this? All operators, so that's the reason not to have any wrong opinion about it. I put the OP labels, particularly on these constants. This is, of course, operator as well, but what is the P? It is m times dx dt. So let me take the derivative in here, m omega c1 cosine omega t minus c2 sine omega t, right? That is what I get by taking the derivative. This other equation enables me to determine it. I think this is a good point to give a short break again. We'll continue in determining the C1 and C2, obviously, because we have undetermined constant operators yet, and we have to determine them before proceeding any further.